We are live.
Hey,
Hi. Go ahead.
good morning, everybody. It's another edition of All Things 3D. Today is December 16th, 2014, Tuesday, and our episode for today is 3D from above. We have some special in-studio guests today. I'm your co-host, Chris.
Hi, and I'm Mike behind the, I'm actually producing this from above, and I'm not doing too good of a job right now. But essentially, I'm right here, and I'll come to myself. I'm a little bit above the earth right now. Might be a little hard to breathe, but I think I can handle it. I got a little oxygen mask underneath the desk here. I took the whole desk up with me. It's got little retros. No, I think we need a little bit more than retros. Yeah. Okay, and we also have two other guests. We have Mike and Jesse from, let them introduce themselves. Go ahead.
I'm Mike Stanton from MBS Land Surveys. We're a local land surveying firm here on the Central Coast of California. And we produce ground surveys with various means. We've got robotic total stations, RTK GPS. We also do control for photogrammetry. We produce terrain models and 3D drawings for architects here locally, and also slope analysis for planners and architects. So our range is probably from LA to San Francisco, basically, for the state of California.
Great. Jesse?
I'm Jesse Brady. I work for Mike here. Yeah, we do all aspects of land surveying. I, at one point in my career, did a lot of laser scanning using Leica scan stations. I do primarily a lot of construction staking at the time. But like I like to say that surveyors, we've always worked in a 3D world. A lot of times it's just displayed in a 2D flat surface, but we have to get the buildings built and they're all three-dimensional. So our minds are always going in 3D, and we have to give that to the rest of the world.
Awesome. Well, thank you so much for being on the program. And we have one more guest.
I'm Robert from Central Coast Aerial Mapping. I'm a certified photogrammetrist. Been doing mapping for about 20 years.
Robert, could you come to your left a little bit, please?
Sure.
You're a little bit out of the camera. And you can see yourselves up there. So,
yeah, so we work with surveyors like Mike and engineering companies locally. We create 3D topographic maps. I've been work with county surveyors and private industries. Yeah, so we basically create expand maps for engineering companies around the area.
Very, very cool.
Can't wait to find out more about this.
Yeah.
Yep. Well, this was what I was hoping. We'd have a nice discussion about this. Chris was asking earlier, and I'm going to be disembodied right now, but Chris was asking earlier about, are there people doing this kind of thing? He's had some interesting ideas on doing topos and then creating tangible products from that. And he's already talked about it when we were off camera about the M-Core printer. So hopefully we can bring that up a little bit more. So hopefully this will be a nice opportunity to maybe generate some interest and maybe even some business. So, okay, so let's go on to our first topics. World is seen by a self-driving car. Everybody seen that? And now I don't even have them in the order. Okay, here we go. So I've got two things. I think I'll play the YouTube video first, and then we'll go from there. So it's kind of an interesting perspective, and this kind of, I don't know, maybe we can talk over it a little bit. But essentially, I guess this is somewhat of a flyby. So what do you think is going on here? These are, I don't know what self-driving car they're using here. Does it indicate in the article? Did anybody take a look at that?
It looks like it's doing a 3D real-time laser scan of the area.
Yeah, that's definitely a point cloud.
Yeah.
Well, I know that's how the Google automated car works. There's a LIDAR system that they have on top. But imagine, this is in real time. Jesse, you remember back in the day, you essentially get a point cloud, and then how long did it take before you could actually get a mesh? So I think that's pretty cool. And the article itself, if you had a chance to look at it, was out at Gizmodo, and they kind of talked through it. They call it the Nokia's 3D mapping division had done this. And it talks about 700,000 points. That's about right, huh, Jesse?
Yeah.
And And as they say here, GPS cameras and a LIDAR system, 32 laser beams. It's a few more than what we're familiar with. And yeah, essentially, as mentioned, is the Google self-driving car works very similar to that, and it's a pretty cool system. And the reason I brought it up is that this is essentially one of the techniques that we're going to be talking about today, which is the LIDAR system. And here we can literally, if you remember, it used to be this huge monstrosity, and now it's these smaller compact units that you can put on your car. Pretty soon they're going to have them in the rear and the front of your cars, and then protect us, put us in a little space bubble. So our next item, and if anybody, let's see, which item are we on now? Posterity. Okay. So posterity is priceless in 3D cartography in India. Did anybody get a chance to read this article? Anybody? Bueller?
Bring it up,
Jesse. Huh?
Bring it up for us, Mike.
Oh man, I wanted to cut to you guys. Okay. So that's what I get for sending this out the night before, huh? Well, essentially, somebody has taken this tool called STL Generator. Jesse, Mike, are you familiar with this? I wasn't either until now, so I'm going to try it out. But essentially, you can take coordinates and it will pull information off of Google Maps. And we've talked about, or either Google Earth, one of the two. And we've kind of talked about that not being the most precise or most accurate or the most detailed, and hopefully in our discussion later on we'll explain why that's the case. But obviously this is free, and if you wanted to go to a particular area, you could literally download using this little app and create topos and then print them.
Is it in full color?
Let's see. Right here it doesn't look like, because it was done on a MakerBot, but I don't know if this is just an image or if this was actually printed. It looks like it's just an image, but I don't know why it wouldn't be. But if it says it's an STL, STLs do not do color.
No.
So more than likely that's not the case. So you would essentially have to do the STL and then do what they call a projection maption of your texture on top, which would have some problems with deformity. But I've been playing a lot with that lately with something else, so it can work. But the fact that there's a tool out there, then it seems to look fairly easy. Essentially, in fact, it looks like it's a web app. You put in your latitude and longitude, and then identify the number of divisions, center your view, and then you create your STL file. Gee, can't get any easier than that. You guys are going to be out of business pretty soon.
let's get a name of this app. I want to check it out when I get back to the office.
It's called STL Generator.
But what's the website? Where can I, like, do they have like an actual website?
Actually, I do not know.
This actually looks very similar
Thatcher C.
to something we've used before. It's with Global Mapper, and there's a website, I think it's from Geocom, and you can actually download the DEM, which is the same digital elevation model that's from the USGS maps. The accuracy isn't real good, but it's public information. Anybody can download it and create your 3D model just from the XYZ coordinates.
And is Global Mapper, what kind of cost is associated with Global Mapper?
It runs about $400, I believe.
Oh,
yeah, so it's not too bad.
So for somebody that's a professional, it's definitely within reach.
Yeah, definitely. Yeah.
It's a great tool for import and exporting multiple formats of 3D data. It's really valuable.
And let me ask you, does Global Mapper, will that provide you the color information like in a VRML? Will it overlay color for you, or is that something you have to do in post, like after you have the 3D topo information?
I believe it will handle that. It's real robust, and the developer's real hands-on. You ask him if you need something, and he'll reply to you the same day and get back to you and saying, "I just gave you an updated, beta of the software that will do this." He's pretty amazing how hands-on he is. Yeah.
These developers now, a lot of the coders are on GitHub, and it's like it's like the world's largest code repository now.
Yeah.
And the developers, you can see how often they log in and like when they're putting push and pull requests to the code base. And so what I found lately, there's this thing called change tip where you, if you have Bitcoin, you can actually tip people on GitHub. Developers, you can tip them, so you can kind of bribe them to to implement features or whatever. It's a good way to, it's a good way to like kind of
great motivator.
It is because all the programmers, they love Bitcoin. It's like
So let's move on to the next item. I thought this was interesting. Part of what we're doing is 3D above, but how about 3D below? And essentially, they've created this little robot. I'm assuming it's a UAV little submarine, and they're mapping. And I don't know if they actually identify the technology underneath the ice structure at Antarctica, and they've determined that it's actually thicker than they thought. So again, people are wrong, only because the tools that we're using aren't precise enough. So it's called the seabed, and it can plunge to 100 feet. And then what does it say? Creates 3D maps. Does it do? It doesn't. It doesn't really tell me what the technology is, and I tried to find a little bit more information out at the location for this, and it's obscure. There's a paper on it, but I'm assuming they're using sonar or something of that nature, and then just mapping it, and maybe even using stereo sonar, using 2 pitches, and then using that to triangulate and come up with the depth point. But I'm just speculating. Obviously, there's a paper out there. These links will all be in the show notes on YouTube, so if you have more interest in it, go out there. But I just thought it would be kind of an interesting break. We're going to be talking about how do we actually get our topos of our Earth, and talk about that in our roundtables. But obviously, we can also map the terrains below the sea and using ultrasonic or sonar to do this. So anybody else want to provide any feedback on that, or do we move right into another item?
We pretty much stick to the ground topography if we can. There is a guy here locally, Robert Reese, who's actually a underwater surveyor, and he's got some very specialized equipment. The applications in this area are probably pretty limited, but he does go all over the state of California. One application would be, like, for example, reservoirs get a lot of silt built up, and he'll go and he'll get to the point where the capacity of the reservoir is limited. He'll go in there, do an underwater survey, terrain model below the surface of the water, and actually can calculate, help agencies determine when those reservoirs are losing capacity, when they have to be dredged, and that type of thing. But anything below the water, we pretty much draw the line there and let him handle it.
What's interesting about what the oceanography and ocean-based stuff, obviously probably not with that submarine, but with all the other stuff, it's all still controlled by GPS. They get their measurements on the surface via the satellites via GPS. So it's pretty amazing. I remember I think it was in May of 2001 was when Clinton switched on the selective availability. He turned GPS on for everybody, which is probably what may come back to be one of the most profound changes in modern society, because we now all have GPS in our cell phones that's plus or minus 30, 40 feet. Before that, it was plus or minus 400 or 500 feet. The only people that had high accuracy GPS were surveyors, because we had to pay $60,000-$70,000 for that. But now that's changed significantly. So it's amazing that pretty much most of our measurements, any large scale, any aerial stuff, any large scale stuff, it's pretty much all controlled by GPS nowadays, which is
I bet the
quite interesting.
What kind of pissed that day? They're like, "Can I get a refund?"
Well, our stuff is still a lot better.
Yeah, and hopefully we can talk about that a little bit later. What makes yours better? Obviously, there's some techniques that hopefully you guys can shed some light on that. That just because you have a cell phone doesn't mean you have that accurate of GPS. And then we can talk about the precision that you normally have from a cell phone versus what you guys are working with. All right, so let's kind of move on to our next item. This might be right up your alley. Well, I don't know. I don't know if you're going to launch into space there, Mike, but I don't know if you guys followed the Rosetta spacecraft. Anyone?
Definitely.
Mm-hmm.
Well, I did. And I found that it was extremely interesting, and I've already jumped
checking these out.
But we're going to talk about using aerial photogrammetry in order to determine depth information. But I would think you could use the same thing if you're orbiting a planet, or in this case, a comet, which is literally what they did here. And they essentially took images and took multiple images, and then they were able to take that information to derive depth information. So if you all brought your anaglyph glasses, we can all enjoy a 3D object here. You in the audience, grab them. You can see it in 3D. But there's another site, and I didn't bring it up, and we talked about it on one of our earlier shows, that has taken this 3D information and printed it so you can literally hold it. In fact, they were using it in planning to determine their landing sites, which I thought was pretty cool. Now, what if they would have had this on the moon? You know, they was kind of like, well, we think that because of the shadows on the moon, this is the depth of the craters until they actually got there. And we had similar issues with Mars. But now we're able to use same techniques that we use here in order to create that depth information and print it out and actually use that as our model. So I think we've moved a long way, or maybe not. But anybody else follow this story from a different perspective than we do from 3D printing? Mike, you want to add to this?
No, I think it's a pretty amazing technology to think of the distance we're transmitting this data and then be able to get something this accurate. It's just absolutely amazing. Maybe Robert could develop a topographic map for the comet. I don't know.
I could launch a UAV up into space.
Yeah.
Start mapping planets. It is truly amazing that you can take photogrammetry in literally anywhere and map nearby objects, faraway objects, ground-based objects. It's pretty much limitless what you can do with photogrammetry.
It was a 10-year. They shot this thing up 10 years ago to get to, it just blows my mind.
Yeah,
it's the dedication of NASA. A lot of people complain that NASA's money just gets blown, but I don't agree with that. But I came from a kind of a space family way back when. I remember when they're still obviously debating, did we actually go to the moon? And I had some nice NASA prints, and I got on the radio. Like, I don't know, I was maybe 17 or something, and first time that I thought myself in public, and I blew it, just like I'm doing now. But but it was kind of neat, and those illustrations were so crisp that they brought back. Obviously, these were reprints. Otherwise, I have lots of money stored away somewhere. But no, that's not the case. So we're going to move on to the last item, and then that kind of will segue into what we're doing today. And that's White Cloud creates full-color 3D printed topography from aerial photographs. Hey, this kind of rings a bell, doesn't it, guys?
Yeah.
But essentially, I guess MindBridge Software teamed up with a 3D printing service, White Clouds, to print and obviously they picked something that was really detailed. Yeah.
And a lot of topo.
Looks like a piece of clay that they. But essentially, they talk about. Hopefully, what we're going to talk about today is that Mike. One of the reasons that I brought you in here is that you and I kind of go back a few years, and I don't remember what year it was, but you brought in this huge object, if I remember correctly, this huge board with something similar to that. How many years ago was that?
That was probably about a decade ago, probably in the middle of probably 2004 or so. And the way that came about was we were working on a fairly large project on the coast. Everybody's probably heard of it, Hearst Ranch. And there was a desire to create a 3D
for our audience, because we do have a lot of people that aren't even from this country who check in. Hearst Ranch, there's something with, I guess, our own castle for the United States called Hearst Castle, which was, if I remember correctly, the newspaper tycoon who had loads of money and decided to spend it on something obscure, making his own castle out here on the central coast of California. So Hearst Ranch is obviously a large acreage area, and obviously there's a lot of needs for surveyors. So I'm sorry to interrupt, Mike, but go ahead.
No, that's all right. Yeah, so this is the site of the Hearst Castle. It's world famous. And the client, Steve Hearst, had a desire for a 3D model. So we looked around, found a firm that would do it, and it was actually created with some of the sources of information that are publicly available. If anybody's heard of USGS, that stands for United States Geological Survey, they created maps all over the whole country, topographic maps of fairly large scale. So these are viewed at 1 inch equals 2,000 feet. So fairly crude, but still the 3D information is really valuable because it can be publicly available, downloaded, and anyone can create your 3D model from this public information. So from that information, we were able to create the 3D model in a computer. For example, application like AutoCAD can create the 3D model. And from that, they actually have a foam base, and then they can actually cut this foam base to the terrain. And there's also some 3D printers that have the print heads that can move up or down with the topography. So just maybe a couple millimeters above the surface of the model, they can actually spray paint the the photography onto the 3D model. And the product was so nice that Steve Hurst actually ordered a second one for his office in San Francisco. So we were pretty happy. He was real happy with the product.
That's awesome.
Yeah, and this was several years ago. Obviously, the expense probably is less now.
Right.
But what I had playing behind you or over you, Mike, was this program called Muck 3D. Have you guys heard of this?
This is new to me.
Yeah. So it appears that this is an application specifically for the purpose of creating tangible topos. And I'm not familiar with it, but it looks interesting. But obviously, as you said, Mike, if you have AutoCAD already, a lot of these tools are already built into it. I don't know, at least from the AutoCAD application itself, what kind of 3D visualization tools. I do know about 3D Studio, and you can get an entire suite, but it's extremely expensive. Has the tools in 3D CAD itself, or 3D CAD, Autodesk, have they expanded in that particular area?
They're
still mainly a 2D.
They're definitely going towards 3D. It pretty much is in 3D. I mean, you're working in 3D now. You almost have to dumb it down to get your, for us in surveying to point our points and stuff. If we don't want to be working in the 3D, or a lot of times for deliverable to clients like the architects, we have to actually dumb the drawings down for them to be, a workable product for them. But definitely the industry is going that way. For visualization, it's an environment that's now you can orbit and spin around and look at your terrain models in 3D. So it's definitely gone that way. So that's what they're the developers are going at. And it sure it has its uses for larger scale projects and larger firms, but a lot of what we do is just your mom and pop house survey, or they're going to do a remodel or something, and that's the information which it's too much. You got to dumb that down to get it to the actual.
Well, that
use.
We're going to get into our topics here in a moment, and but I'm thinking this is where tangible, and I think this is where Chris is alluding to, being able to touch and visualize something in front of you. Put a little house on a hillside does a lot more for the brain than providing them a topo, which is mainly lines with the elevation. How many people know what that is? I mean, before I came to RM Design Group, I had no idea what that was. It just looked like some obscure painting or drawing. But obviously you can learn about that, but most people don't want to spend the time or have the knowledge or even care about it. But if you can print something out, I think that works out really well for somebody. So on that note, we're going to go ahead and move right into our actual topics. And the first one that I want to kind of bring up is, a lot of people are familiar with Google Earth, and a lot of people have done flybys. But as we saw earlier in one of our topics, there is a tool out there, what is it called, STL generator, that allows you to take information from Google Earth. But let's see, I'll start with you, Robert.
Yeah.
If you're familiar with Google Earth, what is its advantage and what is its disadvantage, especially in a professional market like yourself and Mike? So I'll go ahead and move to you, Robert, and if you want to expand upon that, and then we'll just go around the table in the counterclockwise direction.
Yeah, we use primarily Google Earth. It's great for planning purposes on our end. It's more of a navigational tool. I mean, you don't really get engineering grade quality with it, but for planning a flight, for 3D mapping, it's invaluable. And being that it's actually free on top of it is pretty amazing when you think about it. Before Google Earth was ran, we used to have to use 3D quad maps, which were, they were okay, but it was you didn't get the amount of detail you got with Google Earth. We could see what's on the ground, what needs to be mapped. how urban, you know, a certain area is, how many houses are there. We can see exactly what's there. Before that, we had to rely on quad maps, which really didn't show any of that type of information. So it really helps us out in that way a lot.
So have you guys worked with tools that allowed you to extract information from Google Maps? Have you worked with that? I know when I was at, again, bringing up RM Design, but I had played around with it working with the planning department. Some tools, either it was 3D Studio or some other tools that I found online, some obscure open source tools. And I was able to actually pull information out. Plus Google Maps has their own tool set that you can actually draw and add architecture to it. And I had worked with some group to actually create little simple blocks that you could put in Google Maps and then you go out and fly around it. So it's kind of neat. So Mike, why don't you kind of expand upon it? Is this useful for you?
Yeah, oh, absolutely. We use Google Earth every day. I mean, it's just a valuable tool for surveying. And one of the neat little tricks I've learned with it is you can actually take a TIFF file or a JPEG and actually import it into Google Earth. And it's a little tricky. You have to rubber sheet the image in order to get it to correct scale. And I wish it had a feature where it could scale everything uniformly, but it doesn't. You have to scale the X and the Y axis separately. So it takes a lot of trial and error before you get your rubber sheeting where it should be. But what I do, for example, for projects is everybody wants to know, well, where are the property lines? There's no property lines on Google Earth. How can I get those on there? Well, you can easily take the image, bring it in, and you can adjust the transparency. So you can adjust that transparency down to about 50% to where the images, you can see the black lines of the property lines, but you've also got the color image of Google Earth in the background. You take that image, you drape it over the ground. Now you've got property lines in 3 dimensions. So you can see the property lines, how they drape over the mountains, how they go through the valleys. It's just really a valuable tool. And a lot of my clients don't realize, you know, how steep the terrain is. I can set that up. I can make a nice oblique view and then take that to, you know, a photo editor, edit it, give it to the client as part of a, you know, proposal. But yeah, we use that. There's also a tool for getting distances and just rough areas with polygons on Google Earth. And we use those, like I said, almost daily.
You know, just to follow up on that too, there is a pro version you can purchase of Google Earth. That gives you a little more tools. It does have built-in parcels that you can load on there, but that you got to pay about $400 a year for that. And then it has a couple other features where it calculates area, like internally. The free version won't calculate area, but the pro version will. So it's if you're using parcel data a lot, the pro version might be worth it. It's about $400 more.
Yeah. Gosh, it's over 10 years, but the pro version was available then too, and it also had video tools. So if you wanted to create animations, you had that capability. Plus, at that particular point, the plugins that you could work with SketchUp to create your tangible objects to put on, or the 3D meshes to put on the Google map was available in the pro version as well. But I think a lot of those tools are free now.
I've used it a lot of times. Like I said, like Mike, I use it every day. You can make a KMZ file, so you can take coordinates, let's say from Caltrans.
What's a K?
It's a data file that you can use to you store it in Google Earth, and it gives you data point locations. So
it's specific to Google Earth.
Yeah.
No,
I think it's a universal. I think it's a universal.
It's a text-based file.
Yeah.
It was actually Google Earth. Google purchased a company called Keyhole, and Keyhole is the one that actually developed what was before Google Earth. It was called Keyhole, and it stands for like Keyhole. I don't know what the abbreviation of it, but that's where the actual abbreviation came from. Oh, interesting. Yeah, but it's an open file.
It is now, but it originated with Google Earth when it was Keyhole, which was what actually Google Earth purchased it at that particular point.
But I know other software can work with. I think there's even AutoCAD will work with. You can import KMZ data.
Yeah, there's many because as you mentioned, it's become an open format. Many people have used the import feature, but yeah, it was originally derived in Keyhole. Thank you for bringing that up, Robert, and then into Google Earth, which is Keyhole.
So so often we create KMZ files with our coordinates. We need like Caltrans coordinates, monuments we have to find that have XYZ values, state plane coordinates. You create the KMZ file in Google Earth. You put it in your you put it in your phone, or you save it in your Google Maps on your phone. And I've gone down to LA looking for Caltrans Monument, and literally have Google Navigate going to the point, and in a couple instances had it pull up the street view, and you're looking at the street view, looking at the freeway, and it actually I'm looking at my phone. I go, oh yeah, it's supposed to be right there. And then you look up and you actually see the painted up monument with the post right there. So, I mean, it's amazing that that's free. I mean, it's probably over the years, it's probably made us tens of thousands of dollars just in the savings of time that we get. You know, and again, it's a free tool that you get to use. So, I mean, it's Google Earth is Google products in general, and Google Earth is amazing. It saves you a lot of times. You can do things. Again, with the GPS, we can do things that used to take weeks to do. We can do in a matter of days now.
Mike and Jesse, I'll go with the next question right away. You know, we're talking about the benefits of Google Earth, but it isn't the most accurate or the most detailed topos that you can get. There's I don't know, is it a company or a resource, government called USGS, and there may be some other sources that you can mention to me. Why would you use something like that over Google Maps? And I'm assuming you probably still do.
Well, I'll let Robert take this too, but it probably is mostly based on your accuracy. If you want something really rough, like let's say we're working with a piece of land that's thousands and thousands of acres, well, you can probably download the DEM, create a 3D model, and it's probably accurate for some rough planning. But what, excuse me, what Robert and I deal with a lot is, you know, design for civil engineers, architects. They want something, you know, really accurate, and that's where we have to fall back on a ground-based survey. The DEMs, a lot of this data, well, the DEM is a digital elevation model, and this information was derived from photogrammetry. I don't know, Robert, was about in the 40s or 50s?
1940s, yeah. I mean, if the maps have been updated, you know, over time, but it's generally older technology.
Yeah. So the accuracy of a quad map is plus or minus half the contour interval. So if you have, let's say you have an old quad map that's showing 40-foot contours, well, that's vertically plus or minus 20 feet. So that's pretty crude for most people's
like a property line, 20 feet, like especially if your property is only you know, let's say 100 feet wide, a 20-foot 20-foot difference is a big difference.
So it's just used for pretty rough planning purposes, and we get involved with people who need just a lot more accuracy than that.
The DEMs are spaced at 10 meters too, so you know you're talking over 30 feet of point spacing, and there's a lot of stuff that can go in between 30 feet, you know, that you have no information of.
Right. So
when you're talking about engineering type detail, it's not there.
Or plotting the corners of a property line. You still got to go out and shoot the point.
Right.
And my understanding, too is that like the survey points, right, where when you're actually identifying property lines, are not identified by an aerial map. It's based on the corners that have been surveyed prior.
Right. That's a misconception, I think, on the part of the public. I've actually had people call me up at my business and say, hey, I just bought my GPS at Walmart, and I want to go out and survey my corners, and I want to know the latitude and longitude of each corner so I can go out there and set it. And I have to explain to them, you know, it's basically based on the map that was used to create your specific property. There's no national database somewhere that has all these corners stored. Each property has to be surveyed individually because each one has its own unique situation.
And even if you go on like in our county, you can go on to the SLO County website, onto their maps division, right?
Right.
And you can see the aerial basically overlay of property lines.
Right.
But and so what I've done is I've gone out and oh yeah, here's what the aerial view shows as the property corner, but that's not how it works. That's not that it's a rough overlay.
It's very rough.
But and it sometimes could be a whole piece of property away.
That's right.
Where your actual property is, what I've come to find out. So really, if you're looking to get your property, you want to find your property lines, you really need to still have a surveyor come and identify them.
Right. Yeah, I've actually had some property owners that went to agencies and claimed they had a huge encroachment or problem simply based on the GIS level accuracy maps. And I have to explain to them that, hey, look, this is plus or minus maybe 50 feet. Don't get excited about a property line that goes through the middle of your house, because it's just simply graphically represented it. on the database, and probably not very accurate.
Yeah. The other thing with USGS maps is some maps were updated while others weren't, so it's really hit and miss depending on what area you're in with the USGS maps. So you really can't determine what kind of accuracy you're really getting with these maps. They're real more for planning purposes.
So I have a question. When you guys go and take a survey point, are you updating? Are you updating the USGS like when you go? So it's they're on their own, and you guys. So there's no like open standard where you guys can go in, and there's a library where you can basically push a survey into a public repository.
There's state law that that whenever a surveyor sets a marker for a boundary for a property line, we have to file a record of that with the county in which we're doing the survey. Yeah, so that's yes, correct. And so there's several ways we do that. One way is a corner record, which is an 8.5 piece of 11. It's for more simplified surveys that you're doing. Sometimes it's just found an old wood monument and I replaced it with a metal monument that's more durable. The next level, that is a record of survey, which is a more detailed survey that we done, a boundary survey. And then, the other way is when we do a subdivision, we create either a track map or partial map. Those monuments get set in a new subdivision, that there's a record of that filed with the county. As far as topographic data, other than USGS or maybe some of the other agencies that do that data is kept per company. So we have lots and lots of maps in the county, lots of topography that we've done. Robert has tons of it, and we keep that. That's our data that we have. We sometimes get to use that in another project, but yeah, there is no, as far as I know, there's no repository for that. That's our information that we keep in house.
Interesting.
And if someone asks for a map from us that's been already compiled, like legally, we can't release that without the client that paid us for that map's permission. So that's one. We can turn around and get sued for releasing that. They paid for that map, and for their neighbor to come by and say, "Oh, I want that map now," and they didn't pitch in a dime for it.
Right.
So that's kind of legalities you get into.
Kind of makes a little bit of sense.
Yeah.
So I'm assuming that there are many different mapping services. USGS is one of them. Google Maps. Is there anything else that you guys can suggest as far as mapping services?
Well, kind of here again, it based primarily on the accuracy of which and your application. So really large scale mapping, these public sources of the DEM, the digital elevation models would probably work. Once you get down to a few hundred acres, that's where probably Robert would come in with aerial photogrammetry. And the process for that is, I don't know if you've ever driven around and seen those big white X's painted on the streets. Well, that's the control that we set. And those white X's basically are now visible when we fly the plane over and take the photographs. And then those crosses are basically used for orientation in the photogrammetry process to create stereo images. And that's how the 3D mapping is prepared.
So let's kind of go from Google Earth, USGS maps to photogrammetry. What is the resolution of each? Can either of you, Robert, you might?
Robert, which probably...
Yeah, well, USGS, you're talking about 10-meter type resolution, 30 feet. When you get down to engineering scale, we can get down to 1 foot contour intervals with our maps. We can get down below a tenth of a foot accuracy.
And that's the photogrammetry.
This is photogrammetry, yeah. And this is combined, of course, using ground surveyors to give us the control points, reading those control points. So it's pretty amazing when you think about, we can be flying something 1,800 feet in the air and get a vertical accuracy of a tenth of a foot on the ground. And
you're using laser technology, or
no? It's
we'll get into that a little bit later.
Oh, okay.
I don't. We've got 2 more sections, so we'll answer that particular point, Chris. Okay, so essentially you can go from a macro, which is free, Google, and then obviously USGS mapping, depending on the quality, can actually cost some money. I think there's some free USGS DEM maps, but then if you want the nice, what is it, 3 meters? Is there one? I can't remember. Maybe even 1 meter. You have to start paying some money for, and then you'll have to actually go to get services from Robert or somebody like him to provide you even more accuracy. Is that what I understand correctly?
Well, there are some in between services. There's another product called IVSAR. A company called Intermap makes those, and they use some type of radar technology to map the ground. And I believe they're down to like 5-meter accuracy. It really jumps from there down to like photogrammetry type accuracy, where you get sub-foot accuracy.
Okay.
So it's really hard to get. Isn't it really?
And it's still when you're talking ground-based photogrammetry for let's say nuclear power plants or piping, that's still more accurate than the LIDAR. You can get that down to 1/8 of an inch accuracy through photogrammetry.
Yeah.
We should probably mention that the application for LIDAR is really when you have the ground cover of trees, for example. Like one example, about 10 years ago, we had a site in Pomo where we had to do a topography map. And the initial estimates were like $200,000 or $300,000, which was just cost prohibitive. It was covered with eucalyptus trees. These trees were probably 100 to 150 feet tall, spaced, 5 feet apart. And so the question was, well, we need to map this thing. How are we going to do it? And then the idea of using LIDAR came up, and the LIDAR allows you to have an aerial-based system that basically is scanning the surface. And the technology has the ability to be able to scan through the trees and only filter out the short return times and hold the longest return times. So the longest return time to the ground is what gets stored in the database, and it filters out all the tree information. And then you're left with a really good quality topographic map. We went under those after the trees were removed and checked it, and it was easily within a few tenths of a foot. So it was really amazing. So
let's kind of use that as a segue. You're talking about the term LIDAR, and maybe a lot of our audience may not know what the term LIDAR is. We've talked about it before. We talked with a company called Cyark, which uses, who makes it? It's the same company, Jesse, that
Lafica.
Lafica. They use Lafica LIDAR systems. But let's kind of maybe talk a little bit about what LIDAR is. Mike, you bring it up. What does LIDAR stand for, and what is the technology behind it?
Yeah, it's stands for light detection and ranging. And the application is really for, aerial use through a plane. And now, it used to be pretty crude, the aerial-based systems, but now we have GPS that's able to orient the plane in 3 dimensions. So they'll have a receiver on the nose of the plane, on the end of the plane, and also on the 2 wingtips. So as the plane is flying over, it's in real time monitoring the position of the plane relative to the ground, and you're updating that with GPS
And gyros.
Yeah, and gyros. So as it's scanning the ground, it's keeping track of 3 dimensions, the exact location of the plane. And so what it does, it'll pass over like on an area that's got heavy tree canopy. It will take many passes over the ground so that different angles find their way through the trees in different directions. And so for large areas, the LIDAR is really, really good, especially when it's got tree canopy and tree cover.
So also LIDAR can be used on the ground, and we just alluded to that with Cyark using the Lafica ground system. And Jesse, you've got a lot of experience with that. How does that differ from aerial LIDAR?
Well, it's you're basing it off of survey control, your positioning, your XYZ values. So that survey control, is either with a robotic total station or GPS, however you get that control in there. It's stationary. Well, it's both. Take that back. They have both mobile and stationary systems. It doesn't have the range. I think there's a lot of different systems out there. Some systems go 1,000 meters or so. But with the range you get, you lose your accuracy as well. But the ground-based systems, obviously they scan, 60, 70,000 points a second. They're very quick.
When you say scanning, this is a laser scanning type system, correct?
Correct, yeah.
Is it a green wavelength, if I remember correctly, or is it red?
I think some of them have both now.
Okay.
I think they mix the 2 in there.
And the reason for that is air density. Obviously, your green wavelength is a shorter wavelength, so it allows you to penetrate moisture better, if I remember correctly, than red, which I think is the reason that's used. But so you're using lasers, and as Mike alluded to, you essentially are either measuring the time or the reflectance of this off of the object. And by determining that, what they call it, time of flight, TOF, that allows you to determine the depth of the object, correct?
Yeah, the distance from where it's set up at. Yes.
Yeah,
And how many points did you say?
The new systems are ridiculously fast. They're 50,000, 100,000 points in 1 second.
Wow.
You could scan this room in seconds.
Or like that one that we just saw earlier that was 700,000 points per second.
Wow.
Yeah.
Per second.
Yeah. So
Well, and that's important because if you're going to use these LIDAR systems in real time to provide 3D mesh information to determine where there's a solid object, to determine when the car should stop or not, I would assume you'd want it to work very quickly. Otherwise, it wouldn't be any better than a human being.
one of my my good friends works down south for a big surveying firm, and they just spent 1.3 million on a ground-based mobile system that they have mounted to a Suburban, and that includes the GPS receivers they have that mount on the vehicle, and they can go 35.
Now, when you say mobile, an actual vehicle LIDAR system.
Vehicle LIDAR system. They can drive at 35 miles an hour, collecting, I think, about 1 million points a second. They can drive down the freeway and they can collect that without using without using survey control, just with using just the GPS. They're plus or minus 1500s without using it. Now, when they go and they traverse through that corridor, because they're typically using these for corridor work, when they traverse through that corridor and they add survey ground control into it, they get it down to plus or minus 400ths of a foot. So that's what $1.2 million gets you. so it's still very costly. It's cost prohibitive for many surveying firms out there. But it's definitely getting cheaper. That technology wasn't even around 5 years ago.
I'll show our audience. This is all I can afford. This is my micro LIDAR system. No, actually, it is somewhat of a LIDAR system.
And hey,
This
these
is a
are
struct-
evolving pretty quick, I think, Mike,
Well, this is a structure sensor which is based on the Kinect, which is also a laser-based projection system, but it can do this room, but that's about the extent of it, and the quality isn't. Well, it's pretty good.
It's pretty good,
But,
especially for small objects.
Especially, considering this is about, including the iPhone, about $1,000.
Right.
So pretty soon you'll be able to put it on your head. In fact, we've been working on it. I have a head-mounted system, so people who are blind can use it to map out their locations.
Well, and I think there's something. I watched a video recently on this whole point cloud managing the actual data file itself. There's limitations on the hardware because there's, you can imagine 700,000 points per second. Being able to process and store that data, these files are.
Now, let's kind of talk about that a little bit. That's a good point. You have points, which are just literally points in space, 3D space, but that's not really a mesh.
But also with the color value. So not only do you have a geospatial value of where that point is in relative position, it's almost like a pixel in a picture. It's also got to have an RGB color value. So you're talking at 700,000, points per second. You're talking about a massive amount of file bandwidth. So the company I was looking at, they were talking about some tenfold increase in being able to read and write these files. Can't remember off the top of my head who this company was, but I think, again, even with your system, Mike, you're looking at the system itself. I don't think is really limited on.
Well, I don't
think it's limited so much on the actual sensor now. I think a lot of it, the process of the file and the file creation, is limited on the actual hardware itself, like the iPhone.
It's a combination of the two, but it's a good point. And believe it or not, and a lot of people say, you got a supercomputer in your pocket now. I guess depends on what year you're talking about a supercomputer. But essentially, you've got a fairly robust, powerful machine in your pocket, and the latest version pretty much provides the same power as last year's iPad and an iPhone 6 or 6 Plus, and it can compute about 1 million points, which
is a lot.
Something to
but
sneeze
this
at.
technology now, this is like some of the only technology I know of. That's like has a practical application, everywhere. that we're finding the limitations. I mean, you can run these video games that look like real life.
Yeah. Well, let's kind of get into that a little bit. Maybe I'm going to
Yeah.
drop back to Mike and Jesse on that. What do you guys use? I mean, I remember, well, dating myself back at RM Design Group, that I tried to get you guys the beefiest machines possible because you had to do a lot of crunching. And if you remember, I created that little ad hoc visualization team there, and we crunched a lot of this. In fact, before I left there, I was planning to create a render farm because we couldn't keep up with it. I mean, they would essentially start them in the evening, and the next morning they might have a file done for one frame. And then when we did animations, it would run like all weekend.
Right.
So what are you guys working with?
Well, pretty much just the state of the art, top of the line Dell machines for 3D work. And, the software is pretty much kept up. What's interesting is the software is just so much quicker now. They rewrote the software for AutoCAD. We now use something called Civil 3D, and it is just light years ahead of what we had just 10 years ago. I remember in the 90s working with a 10 megabyte three-dimensional file. The guy would open the drawing, literally take a coffee break because it would take 20 minutes just for the drawing to come up. And now we're talking about just fractions of a second. And now with scanning, we're dealing with millions and millions of points. And, the analysis of this and processing is literally taking, less than a second. So it's really, really come a long way in the last few years.
And part of that too, and Chris, you just kind of identified it a little bit earlier there, that we now can use graphics cards, or the same thing that power our video, to do a lot of this. You're maybe familiar with the term CUDA cores from NVIDIA. And there's also, I think, OpenCL or something like that as well, that provides something similar to that. That allows you to use the parallel processing functionality of the graphics card in order to increase the performance. And I'm pretty sure Civil 3D has a switch to turn that on, if I remember correctly. Is that right?
It does use GPU
okay.
rendering, GPU hardware acceleration. I think that's one of the things I think we're going to the LIDARs. The hardware to generate the LIDAR is pretty advanced. I think what we're starting to see is the software trying to catch up to how to deal with all these points, the post-processing of it. And when you're capturing, like you said, 700,000 points a second, you're dealing with hundreds of millions of points.
Sure.
That the software
Robert,
has to deal with.
Speak more into the mic.
Sure. Can you hear me? Okay. Yeah. So you're having to deal with hundreds of millions of points. We do the same thing with aerial LIDAR, and it's more I think of a software issue now that is becoming the issue with LIDAR.
And I think this is another point on that, is this is another room where I think a lot of like electronics engineers can get into is the idea behind ASICs, like basically application specific hardware. So you'll see, like, I hate to go back to it, but Bitcoin mining, right? They started making these, they were using GPUs to do it all, but then they started making basically processors specifically geared towards it. And it took the Bitcoin mining thing to the whole next level and basically made it 100 times faster and way cheaper, uses less wattage, etc. So, but I think this is a whole other realm for these people that are developing hardware, that, hey, LIDAR is a thing. You're going to see more and more of it, whether it's in surveying or, shooting satellites to comets or whatever.
Yeah.
And maybe we need to develop actually processors or, hardware that's specific per application.
For processing.
And they're actually moving in that direction. And NVIDIA has rack-mounted stuff that's basically a bunch of CUDA cores and their processors to do just exactly that. And I think they have a special chip for NASA themselves for processing. So we are seeing that being used now. It's funny how we went from creating more realistic video games to being able to use these professionally. So let's kind of go into the next item. We talked about LIDAR, which is using light in order to determine depth information. And if you're familiar with the Kinect, it's very similar to that process. But now we're going to get into photogrammetry. And some of you out there may have experimented with Catch 3D, which is an Autodesk application that you can get on Android, iOS, or your PC. And you would literally take a bunch of photos around an object, and then you use the cloud to crunch it and create a 3D object. There are some caveats. You got to make sure your color balance is correct or your lighting is correct. So there are a lot of things you got to work with, but it's also the same technique, and hopefully Robert, Mike, and Jesse can kind of expand upon it, that it's used to map terrain. And so I think I'll just push right into Robert, if he could kind of give us a rundown on what photogrammetry is and how is it useful to create topography.
Sure, it is really roughly the same what you're talking about. The only difference is you're applying a 3D coordinate system to the terrain in photogrammetry to derive data, terrain data from it.
When you say 3D coordinate system, you deriving from GPS or triangulation methods?
Deriving, the surveyors are providing the coordinate system for you by placing these targets on the ground. And once you take the photography, you actually read in these visual panels that you see in the photograph. And you basically coordinate, you correlate the coordinate system to the pixels of the imagery. So you'll know a certain distance you travel on the ground will be a certain amount of pixels in the image. And that's how you can basically create a 3D topo map.
Okay, so essentially, how many images are you taking per second? And then from that, you can determine how much you've traveled, correct? So if you know your speed, you'll be able to determine, or is that all based on markers?
It's not really based on speed. It's just more based on stereo coverage of the amount of terrain you want to grab. Depending on the amount of accuracy you need, the higher the accuracy, the lower you have to fly. So if it's a big area, you technically need more stereo overlaps of imagery.
When you say stereo,
yeah.
What is the actual distance? If you talk about stereo from 3D movies, it's the interocular distance between the eyes, which is I can't remember.
This you take
60%
overlaps of the imagery.
Okay.
Yeah, that's to create a stereo model. So basically, the overlap area is your stereo model of the terrain you want to capture. So let's say a 10-acre parcel would fit in one stereo overlap at 1,800 feet, and from there you would need 5 ground panels to correlate that image to do mapping from, which the surveyors would place on the ground.
Robert, it might be interesting for people to hear about how photogrammetry was done, say 10, 15 years ago, with basically each eye on a stereo plotter versus now you're using soft copy with a dual screen, 3D glasses where each eye is focused on a particular computer screen. I mean, it's just amazing how much that's changed.
Back 15 years ago, still, they were using 9x9 film that you'd place in these giant instruments, each one, and you'd have goggles that you'd look through to see stereo, and it was actually had optical mirrors inside the machine that would reflect off to see these two imagery in 3D. Everything's done digital now, so you wear if you've seen a 3D movie, it's real similar to that. You throw on the 3D glasses, and all of a sudden you get depth to basically derive the 3D data.
If you look right behind you, my little friend here is wearing a pair of anaglyphs, but the screen up there that you guys are watching is using a technique called polarized circular polarization, and that's what most of the movies use. And then there's another technique called shutter. So I'm assuming it's something like that you guys are working with.
Yeah, we're using shutter active glasses where the interval rates of the refresh, or each eye has a different interval refresh rate. So each eye is seeing a different angle of the photo to give you the 3D effect.
Pretty cool. Well, with that being said, you're just telling us what you could see in a movie. How do we derive or take that information, the stereoscopic images, and create a tangible object or a 3D mesh?
It's actually done in a manual way. When you throw on these 3D glasses, you see a point on the ground in stereo. And you can actually move this point around, and you can move the elevation up and down until you hit the ground in 3D. And the operator then can make a 3D break line describing the terrain, which goes directly into a CAD station like AutoCAD to describe the terrain. And from that, once the whole terrain is described, you can generate contours.
So it's still a manual process.
It's still a manual process, yeah.
I've only used it once, but I remember using the manual system. It was like the little dot you're looking at was blurry, and there was like a parallax going on, and then when it was no longer blurry, then you were on the elevation.
Yeah,
so that's
when you get really good at looking at it, it looks like when you're below the ground, the point will you can actually see it go underneath the ground. You look like you're not on top of the terrain, and when you come above, you can actually see the point float towards you above the terrain. So it takes a lot of practice to get it down really well.
In the old days, you had little like rotating knobs. I'm assuming now it's a mouse. I mean,
it's a 3D puck. Yeah, it's a 3D puck.
Okay, so what's the company that makes that? Do you remember?
3D Stealth Mouse.
Oh, I heard about it, but I don't have one. I've got the other one, which is like a joystick. I can't think of the name of it.
Yeah, there's several companies.
The Connection. You have the 3D Connection.
I've got 2 of those.
Yeah. So I think they actually make these pucks for like 3D software also. If you're doing 3D
right, that's what I've got. I've got 2 of those.
Yeah.
Okay.
It's the same type of pucks.
Yeah, you actually lift it in order to get the Z, and then you rotate it X to get your X and Y.
So if you're looking like at just a 3D modeling mechanical software, it's the same idea where you can move your Z. But this one you're looking at in 3D stereo to move your Z up and down.
To actually adjust it.
To adjust it and to
actually manufacture the 3D file.
Exactly.
And then you output. So then the 3D file. What is that most commonly used for?
We output a DWG file, which is an AutoCAD format file, and usually we'll go to the engineers. Once they have a DTM surface, they can do hydrology studies to see how water flows. They can do earth volume calculations. They can do all sorts of stuff with a 3D model once they have a surface model.
So they bring it into AutoCAD, and then they can build their plant. They can plan their building.
They can generate contours on the fly once it's done. You can do multiple things. It's a vast amount of data you can do with it. Stuff you can do with it. It's pretty
used to just deliver contours, right, years ago, but now we get up to like 3 deliverables. One is the orthophoto, which is basically high quality, true to scale color photograph with down to 0.2 resolution, pixel resolution. Then you get your contours, and then he can also deliver the 3D wireframe. Okay, so you get a lot more for the same product we were buying 20 years ago. You get a lot more data.
Yeah, what's interesting, before they used to actually draw the contours directly. So you draw each contour interval directly. Now you draw what's called a DTM, where you're actually describing the terrain by ridges and break lines and points. So then you can generate contours on the fly, whatever contour interval you want, instead of deriving the contours directly.
Which is the same way we derive our contours when we're doing ground-based surveying. We locate the flow line of a creek, the top of a creek.
What do you mean by contour? I mean,
line of constant elevation.
There you go.
And then DTM, we should probably explain, that's digital terrain model. So basically we take the points. The points are used to generate the DTM. Some people call this a irregular network, because really what it is, it's a series of triangles in 3 dimensions. Sure. And then when you put those triangles together, you get something that, looks like this.
It's a surface model.
Right, surface model.
Yeah.
While we're here, do you want to go ahead and talk about some of the things that you sent me earlier?
Sure.
Okay. So this is, if you can see it behind you, this is an elevation, but we may not want to cover that one. So let's see what we have. Here we go.
Okay, here's a good example of a terrain model. This was done out in Avila Beach, California, on an oceanfront piece of property. If people aren't familiar, here in California, views are very important. What people can see is important, and also the slope is important. And so oftentimes people ask us to create what's called a slope analysis map. And you can see there that there's this is composed of thousands and thousands of these little triangles that I talked about, the triangular irregular network. And basically, anytime you have a triangle in 3 dimensions, there is a unique slope associated with that triangle. Well, the software can assign a different color to each slope range. So for example, in this case, we might have the flatter areas in green and the steeper areas in orange, and then we typically would make things over 30%, which is unbuildable, a color like red or maybe purple. So you can very quickly see where the flat areas are, what are your usable areas, and then you can take this and rotate it in different views. Here you can see the plan view on the bottom.
And this was generated by AutoCAD Civil 3D?
Yes. And then we can designate, I think I can't quite see the legend, but I think we've got 4 or 5 different slope ranges here. But really the options are limitless. You could have 10, 20 different slope ranges. And then, of course, the colors, you can assign any type of color you want to those different slope ranges. and then we can rotate these oblique views in different views in order to, you know, see where can I get the ocean view, or where can I see the highway, or where can I see a certain
incredible.
viewpoint.
It's
And
pretty
can you-
neat. You know, it's interesting though. Do you notice? Remember the draw or the images that you see for overhangs and some of the slicers?
Yeah.
I have a feeling they use a similar
Yeah, I mean, yeah, it's definitely
algorithm in order to derive overhangs in 3D prints are the areas that you exceed the amount. You have to have support structures. If you're familiar with FDM printing, you build layers. Well, you can only build so much of a layer out before gravity takes its effect and causes it to droop, or literally causes the
Fail.
model to fail. So they have algorithms, and I have a feeling it's probably very similar to this, because you're actually determining the angular distance that you can use for the overhang. And normally that's what, 60 degrees? I can't remember.
I usually stick to 45 degrees.
40, yeah.
I
Some you can
generally
push it to
conservative.
60, but it does something similar that you get color coding. So I'm wondering if they borrowed that technique. Now, let me ask you a question. If I wanted to, I think Civil 3D has the ability to take this topo that you have here and export it as an OBJ or an STL now. Is that correct?
It's, as the technology goes, there's more and more formats to export drawings into. I wouldn't know all of them off the top of my head.
Okay, but there is a way. So if I said, hey, you just did this and I want to go and print it. And I've got my friend here, Chris. He can 3D print that little acre that I've got. Could you send him the file? You could do that, correct?
Yeah, we could do that.
Yeah,
There's the way.
We can do it.
there's a way.
Okay. You know, you had some other eyes, and I'm assuming there was a reason you brought up these others, and maybe I'll drop back to the, let's see, we'll start with this one first, and I'll come back to it. This is an elevation for something, and there must have been a reason you sent it.
Yeah.
I threw that one in.
Okay.
The reason I did that is that's what clients want. That's what people pay for. It was derived using a robotic toll station, which basically we selected the points where we took the shots. So in the field, I actually spotted the scope like you
Okay.
would any look through it, got the crosshairs on the
like a rifle
on the
or
parapet like a rifle, yeah, and you took the data, located the point at that point.
Yeah, we should point out that this is called direct reflex. You don't actually have to have somebody climb up the building
Correct.
with a reflector. All we have to do is point the instrument to the corner of the window, and it uses direct reflex technology in order to derive the XY coordinate of that point.
Right. It's
So
basically
is there
a scan taking one shot at a time.
Okay, so there's probably a, what do they call it, an accelerometer or a positioning in the device itself. So when you actually point this at this particular, it knows your angle of
Right.
observation, and then using either laser or something determines its distance
Correct.
from there.
Exactly.
Yeah.
And then it triangulates it from
Correct.
Right.
Gets the location. So the client, in this case, the architect, he wanted those dimensions there given to him, but he also wanted a 3D wireframe of the facade of the four sides of the building.
Okay.
So
So that's not what you get here, and I think you gave me another image that has that, correct? Let's see. Is that,
there.
Yeah, this one shows the kind of the challenges when you draw in 3D, because let's say, for example, you're looking at a side view where you're not just seeing that one wall, you're also actually seeing the other walls that are behind that wall. And it gets a little tricky to know when you're actively working on a particular axis in AutoCAD, which wall are you working on. This kind of shows the way we dealt with that is we assign different layers to each wall. That way you can isolate that layer, work on the one wall, and then when you unfreeze those layers, you simply have all the walls,
So how did you
active at one
derive
time.
this 3D information? That pointing system can't see through the building. So how did you come up with
You have to traverse around
Okay.
the building with your total station and
Oh.
take the shots, which was real tricky in that case. I mean,
Yeah,
most of you are familiar with Slow Brew, I'm sure, because you're local. The alleyway on both sides of that is like 10 feet wide, and you have to take sharp angles to shoot the objects using
I was about to say there's an
conventional
alleyway there. So
yeah, using conventional equipment. So it was tricky. Accuracy suffered a little bit because of those sharp angles, because when you're looking at the windowsill at a very sharp angle, you're trying to sight in and hit that spot, but you may be going a little bit left or right of it, so it throws your measurement off, which we noted on our survey that that the level of accuracy was plus or minus a tenth. So that I put that in as example of, you could scan that whole building and you could drive all that out of point cloud data. It may be more accurate that way, but what the client wanted was very rudimentary, very crude. That's the working product, and which is what we see most of the time in using, scan data, is that what in our industry as land surveyors, we're dealing with civil engineers, and we're dealing with a product that's been the same product it's been since I've been surveying for 16 years. They want a CAD file that has contours, that shows the fences, that shows the buildings, and that they use that to do their design, which is then a set of paper plans that gets submitted to the agency for review.
Now, Jesse, we've talked in the past, and we'll talk about the two different techniques. Now, obviously, you essentially point and shot each of the points, and you had your coordinates, and you're able to derive a simple line, three-dimensional object here. But we've seen people use LIDAR and also photogrammetry to do something similar. Why would you use that? As we know, it's more expensive, I'm assuming. So why would you use that?
Well, if you had to do something, obviously that's just a building facade. If you had to do something much more complex, you had to do piping in a refinery or something. They used to do that with photogrammetry, and that got replaced by LIDAR, except for in very extreme cases in which they need accuracy better than LIDAR can produce. That's what you'd use that for. If you had to produce a actual 3D model of, let's say, the refinery and do the piping and extrude all of that, you'd use the point cloud, because you can pick the point cloud and you can have it extrude the pipe, and it comes out as a pipe. So it has its applications.
Well, something else, and I think you actually used it for it, is that we had a fairly, I can't say decent, wouldn't say devastating, but obviously it was a fairly severe earthquake several years ago, and plus earthquakes are something we have to live with here in California. I've heard that LIDAR is very useful for that because it can show stress analysis and fractures and things like that. Is that true?
Yeah, we used it on the San Miguel mission, and we scanned the inside and outside of the mission. By doing that, again, we used conventional survey equipment to get our initial coordinate system. And then we scanned the inside and outside, put the inside mesh and the outside mesh together, and you could see the cracks on the outside of the building, and you could see those same cracks represented on the inside of the building. You could see the thickness of the cracks. You could then, you could see how much the building had moved, how severe the cracks were. You could do that with conventional equipment, but it would take a lot of shots, and it wouldn't be as detailed as looking at the actual point cloud. Once you're in the point cloud, you want the two measurements at the bottom of the crack. You want the two measurements in the middle of the crack on the wall. You want it at the top. It's real simple to do that. So obviously that was a great application of scanning in that instance. So, it's another tool that we have as surveyors. We have GPS. GPS has its limitations. The scanning has its limitations. It has its uses, its pros and cons. And you have to have the right kind of job to actually justify the cost it takes too, because depending on the data you need to get out of the scan, you could scan it and have almost data overload. You have too much data if you're trying to produce something very simplified and very simplistic.
So how much does a LIDAR system cost?
They're about $100,000 if you get the latest and greatest.
So how about your, what would you call it, spotting or your range measurement system? How much does that cost?
They're about $40,000 brand new.
So they're still fairly expensive as well.
Yes.
So being a surveyor isn't cheap.
No.
Because you also have robotic units that you use for triangulation. So that when you actually have to do staking, right? Yeah. Well, I guess that's to replace the human body, which actually could be even more expensive.
Yeah. I would say if you want to be competitive, and let's say you're a newly licensed surveyor and you want to go do your own thing and you want to be competitive, if you bought brand new and you didn't buy used, you'd have to get a GPS setup, which is a base and a receiver. It's 2 units. In this area, if you're down in Southern California, you can get away with 1 because they have networks that are available to
the name public. I hear most of the time is Trimble.
Trimble or Lafica are the 2 leading ones. But if you were to go buy your equipment brand new, you'd be $100,000 out of pocket to go out and hang up your shingle and try to compete with everybody else.
Okay.
Because you're looking at about 50,000-60,000 for the GPS units and another 30,000-40,000 for the robotic total station.
You got to buy a truck too, right?
Oh yeah, and you have a truck. Yeah, I'm assuming you already have a truck.
Yeah, okay.
Man, you guys are making me feel bad that I didn't pay more attention in trigonometry. That's for sure.
Okay, well,
I should have paid better
let's
attention.
move on to Robert, because
Yeah.
he brings a different perspective, and that's photogrammetry, aerial photogrammetry. And I'll have to jump back to the camera for Mike and Jesse, but behind him, or behind them, is a topo that you gave me earlier that I put up on the wall there,
Mhm.
that you did using, I'm assuming, aerial photogrammetry. Is that correct?
That's correct. Yeah, this was all done in Civil 3D also. All these the 3D extrusion and the ortho draping on top of the Rountable there. You see, we've done that about 8 months ago. We flew this at about 1,800 feet, and we were able to track all the data that you see on that. It was really, really fun, accurate job.
Now, does it require a special aircraft to do this?
This was a manned fixed-wing aircraft. Yeah, they have a special digital camera that's belly mounted. Those digital cameras are about $100,000. Oh no, they're hitting about $900,000. Those digital cameras.
That's fairly expensive.
Yeah, very expensive.
So, but you kind of talked about another possibility,
Mhm.
and I'm going to jump right into it. So essentially, you need a lot of equipment. But before we do, we all know about Google Earth, and they use something a little higher than 1,400 feet. They use satellite systems. Is that correct?
Yes, that's correct.
And I'm assuming satellite systems that also do photogrammetry. Is that correct?
You can do photogrammetry satellite systems. We haven't done it personally. That's more derived for, you can't get as much accuracy as with a plane because the imagery is not as detailed.
So how does Google Earth derive their 3D topos?
Their 3D topos are actually derived using the USGS data, is where they get their terrain. And I know they're also starting to collect some LIDAR data to fill in certain terrain for more detailed
All right,
areas.
so you're using USGS, but you have topos around the world. I mean, USGS is obviously US, so are they doing the same thing worldwide?
They're grabbing local data from different regions, exactly.
Okay, so then they're not deriving their topography from their satellites. They're not using...
More and more, they're replacing it with some satellite data and some LIDAR data, especially in real urban areas like San Francisco. They're using LIDAR data now to get really high accuracy in some of these urban areas, Google Earth.
And I know the European Space Agency, I know they just fired up a new, like this is like a unfolding, they're rolling out even more satellites that do this. So I know it's like something that's evolving. LIDAR is getting more accurate from space.
Yeah, and if you can actually turn on their 3D buildings in Google Earth, and it's an option they added probably about a year ago where you can actually see the buildings that were derived from LIDAR directly, and actually shows the
yeah, it's pretty cool. In fact, have you all heard of Google Cardboard?
Yeah.
Actually, he brought we got a German version, but they made it out of hard foam rubber.
The Oculus
but
it's like a poor man's Oculus Rift.
Yeah, it's like a it's like a headset you can put on, and when you look around, it's like virtual reality, right?
Yeah.
But more importantly, you can put your phone into it. So they call it Google Cardboard.
Yeah.
It was made out of cardboard.
You can cut it out of cardboard, put it together, and have virtual reality goggles made out of cardboard.
You know, one cool thing I did, I actually ordered an Oculus, the developer's kit, and they had a plugin for Google Earth.
Yep.
Where you can go into Street View. I don't know if you saw that, and you can actually put on your virtual reality goggles and see the Street View in 3D and make a pseudo 3D view of the Street View.
Look around.
Exactly.
Yeah.
You can look around the Street
I've
View,
had
which is pretty
the
impressive.
DK1 and the DK2.
You have both,
yeah. But one of the points I wanted to make on this Google Cardboard is that you can put your phone in, and there is an app specifically to look at Google Earth from space, and you can kind of fly. And you have this on, and there's no umbilical cord, so you can literally walk around, look down, because you're somewhat disembodied and you're just kind of floating, and then you can use certain hand gestures or facial gestures to kind of swim down to a lower location. And I think one of the sites was San Francisco, so you could kind of zoom through the streets like Superman. So I thought that was kind of, so if you wanted to use for
virtual walk.
Google.
Yeah.
We were talking about it. It's like the Oculus got bought by Facebook, but I would have thought it would have gotten bought by Amazon, because you know, then you could go shopping with your friends. You know, you go to the virtual mall, and
You can totally see that in the future happening.
Like what do you think about these shoes?
Yeah. Well, who knows what Facebook has up their sleeves, right?
So let's get back to the point of that it's really expensive to find an aircraft with the specialized camera. Obviously, you got to have a licensed pilot. You've got to have fuel. I mean, there's really, really expensive.
And you have all the insurance overhead on top of that.
So it's extremely expensive. So if I were to ask you to fly over here and give me a photogrammetry topo of how much would it cost me?
To fly here, we actually sub out to different flight companies around California. We fly all over California using different flight companies. The closest one that has the equipment to fly here is located in Burbank, and they will charge about $1,000 to get up here to fly an area. Okay. So it starts at $1,000.
Well, that's what they would charge you.
That's what they would charge us.
What would you charge me?
To create a full-blown map, it's about $2,300 for, let's say, a 10-acre parcel is what it would cost. It's not too bad.
You forgot the surveyors.
Yeah, right. And the surveyors have to set control on top of that, which I don't know what you guys charge on your end.
So what are we looking at? $3,000 to $5,000?
3 to 5.
For a 10-acre parcel, probably about $3,000 to $5,000.
About right.
So is there a possibility of doing this cheaper? I'm kind of hitting you over the head with my segue here.
Yeah.
You've got something to show us here soon, but there's an opportunity, depending on if FAA will get smart on this whole thing, that something that the military has been using for several years now, and that's UAVs.
Correct.
And so there's a possibility that you could use UAVs, means no cost of a pilot, obviously less cost of fuel, because I think they're rechargeable batteries. And then the camera system would be less expensive because it would be less bulky. I don't know if we have the accuracy there, but there's a possibility of reducing this maybe down into a couple of grand, maybe half that cost.
Yeah, we can reduce the flight significantly once the FAA allows us to start using UAVs to fly local areas. You wouldn't have to, hire a fixed wing manned aircraft with $1 million camera payload to come up here at $1,000. You can launch your own little UAV system, for a few $100s to fly a local area and do mapping from that.
Now, the problem right now is that personal UAVs or even commercial, they have a ceiling of 400 feet, if I remember correctly.
That is correct.
And if I remember correctly, and in previous conversations, what I've read, you need a higher ceiling in order to provide proper photogrammetry. Is that correct?
Not necessarily. The only difference is now you'd have to take a lot more images to get your photographic coverage. You can stitch multiple stereo images together to create your map. So you're basically, when you're flying with UAVs, in a traditional high flight, manned aircraft, you're taking one stereo image. With a UAV, you might be taking 6 stereo images to cover the same amount of area.
Very neat.
Would that require more survey control then too, as well?
Not necessarily. There's advanced software that does automatic image matching. So it's basically taking these really low, high resolution images and stitching them together to get you really high accurate maps. It's still in the testing phase. We're still R&Ding it a lot because we're trying to see how accurate we can actually get with UAVs.
So Robert, maybe you could talk about
something to show us here.
Right.
Let's see how we can do this.
Just take it in the middle of the table.
Yeah, except we'd have to move. Yeah, can you hold that?
Yeah.
Try and, you can see your camera there.
Yeah.
So
this is a prototype of what we've been kind of
exactly with the props off
talking
the back.
about.
So
and it looks a little bit like those big boys that they're using in the military.
Exactly. So we're taking. We have the time to do R&D because the FAA is not allowing us to fly it yet. There are already commercial companies that you can purchase these already made, but they're upwards of $30,000 they're charging for this. So we figured, since we can't fly them anyway commercially yet, why not start R&D and trying to make our own? So we're doing an open source solution. A lot of this stuff can be bought open source. 3D Robotics provides the GPS unit on top of it. If you open this up here, this little guy right here.
That's the same one I fly. It's an APM.
Yeah, the APM, exactly. Yeah.
If you move your body to the left, there
Yeah. So this right here tells the plane where it's at. What we're trying to achieve ultimately is have the plane fly directly from a computer controlled flight path. So you want to be able to launch it, and then the computer takes over, shoots the camera at certain intervals at a certain point, and then flies and lands itself back on the ground. That's where it starts getting more complex.
They call it telemetry, right?
Yeah, and doing it yourself. That's where the complexity is, having the computer start doing it yourself, because you can always launch it and control it yourself. It's a lot harder though.
When you get into automation.
Yeah, and trying to keep a certain altitude with the GPS built in. And this little unit gives you the yaw, pitch, and roll of the plane. So you have these two combinations together. You can tell the plane, go up to 400 feet, shoot an image every 500 feet distance, and then come back and land. And to try to do that manually yourself would be a lot more difficult. So that's where we are at this point, is trying to R&D all this.
And this is all open source now.
It's all open source.
APM board you can buy. Like when this first came out, basically this 3D robotics company, which is a great company out of Southern California, they were the only one making it.
Exactly.
And it was about $250, but now you can buy, because they made it open source. There's actually other manufacturers out there.
There are,
and they have them down to like, I think they're like $85 now.
There are, yeah, and there's a great community out there of people that help each other, trying to get this stuff to work. 'Cause it does get complex when you start combining all this stuff together. We haven't even tested the camera part out yet. We're still trying to get the plane to fly without crashing.
Sure.
Robert, what about the megapixel capacity of the manned aircraft as compared with the kind of camera you would put in this, and how does that affect the accuracy of the ultimate photogrammetric?
Well, of course, the manned aircraft has a really high megapixel. You're probably talking about 150 megapixel cameras on these manned aircraft, versus some of these are probably 16 megapixels, 24 megapixels. Now the difference though is you're only flying about 400 feet off the ground, so you're offsetting that lower megapixel by flying lower. So you're getting a lot more detail by flying a lot lower. So
you can still get, say, 2-foot contour mapping with this type of setup.
I think we can even get close to what we're achieving.
Really?
With yeah, I think it comes down to what it comes down to now is getting the GPS updated more, and the IMU, which in mapping terms is called an IMU, inertial measurement unit, but they call it roll, pitch, and yaw. And for the plane, but it's the same thing. You're deriving omega phi kappa, which is what they call mapping.
Right.
And so you want to get these units have to advance to get a little more accurate in order to achieve.
So the companies that are selling these as a unit, are they using proprietary units that you can't buy on the open market?
No, these are open source hardware units.
Open hardware.
Yeah, which is what's pretty neat.
I mean, like the ones that like Tremble and
they're
using
proprietary, and they're actually they're using stuff from companies that are using more high-end equipment, and that's why it's more expensive. Their units, Trimble's goes for $60,000.
Probably more sensitive sensors.
More sensitive, more accurate. But the open source community is starting to kind of catch up to that. Yeah, right. So it's evolving really quick, and that's why we don't want to make a huge investment buying one yet, because things are changing really fast, and we want to kind of just get the R&D down and see how far we can get ourselves before we go and purchase something.
Sure, yeah,
because we figured, if we're flying this thing and we're paying $60,000, this thing crashes and something breaks, are they going to charge us, $4,000 to replace a wing or something, which we could, replace ourselves if we can get it to work. So.
Yeah, and the beauty of the beauty of the open source too is like, instead of having maybe 5 Trimble guys that are the software lead, the software engineers working on a project, in an open source project you might have 1,000 developers.
Exactly.
So you have a lot more minds, a lot more brain power working on this project. So like the software evolves, I find, a lot faster.
It does.
Like you'll almost see an iteration of the software come out, and they'll fork it. Maybe you'll see like 3 different versions of the software come out.
And if you run into a problem, you got a lot of boards you can get on. A lot of people are probably running the same problems you have, and you can get a lot of answers of why something's not working correctly or not getting the right type of.
Because I know there's like Ardu Pilot is one of the is the one that that's the one I use, but I know there's also like a Ardu Pirate.
Yeah,
and like that one lets you do a little bit more advanced. It's like it's a fork of the project.
Yeah,
and they borrow a lot of the same code base, and they give retribution to or they
Yeah,
they
and the guys
pay,
that make
they pay
this,
homage to the
they actually make their own open source plane that they build, but you can buy from them, called Ardu Plane, and they have a quadcopter too, or a hexacopter, I guess you want to call
Right.
it, that you can buy. And we went with a fixed wing primarily because it has a longer flight time
Right.
versus a quadcopter. They both have their plus and minuses.
Sure.
A copter is really, I think, valuable if you're going to be doing urban areas. You can do vertical takeoffs, which you can't have with a fixed wing yet, even though there's rumors that Google's building a fixed wing that can take off vertically and land vertically.
Yeah, well, and maybe if you obviously you have a little bit more agility with a quad.
You do,
So,
you do.
In a filming application, it would be probably better because you could go exactly where you want without having to keep a certain airspeed. This needs airspeed to keep lift.
It needs airspeed, and we're trying to cover a good amount of area too. The quads usually they go for about 15 to 20 minutes on battery time, whereas this thing will go about 45 to 50 minutes. What happens? You're powering 6 motors at once with a quadcopter or a hexcopter, and this you're only powering 1 motor, and you're getting airlift on top of that, which is really letting this thing fly for a while.
Right.
And
so
almost
just glide it too.
Exactly. Yeah. So
that's kind of nice to be.
I think we're gonna
crash when you run out of battery.
Exactly. I think we're gonna end up having probably eventually both. Once the FAA, the big restriction right now is the FAA. The FAA is not allowing these to be flown for commercial purposes. No money exchanging. It's basically hobbyists can fly these right now, but no money can be exchanged for business purposes.
Isn't it true these are active in Canada right now?
Yeah. Other countries are allowing it. Right now, the U.S. is being held back with these rules, and they want to do it for safety reasons. I understand that there's been instances of these drones getting in front of flight paths of planes trying to land and causing some real big issues there. You don't want to take down a manned aircraft because these guys are flying it near airports and stuff. So they're really trying to determine how we can put out regulations to make these safe. And I have a feeling they're probably going to come out with regulations where it takes into account these GPSs built in, where it has a go home feature. So if the plane starts flying away, it'll come back to where you launched.
Yeah, and I think it's going to demand, again, it's like technology as it evolves.
Mm-hmm.
It demands the need for other technological progress, which
Mm-hmm.
I see a huge loophole in the transponders on manned aircraft.
Mm-hmm.
Right? A lot of aircraft up there are completely outdated. They don't see other aircraft.
Yeah.
That's why there's a lot you have to keep on the radio all the time. They're always logging, and that's what all the flight control towers are all about, is like keep making sure that everybody's at the right elevation. And this thing's automatic. You could essentially, if everybody's transponder was up to date, you could set an algorithm so that there was no such thing as a mid-air collision.
Exactly. And they're talking about building sensors that are sense aware, where other objects that are around you, other planes that are around you, and avoidance systems for these things. So it still has a lot of evolution to happen, but it's coming quick. And I think what's the problem is the FAA is really trying to wrap its head around the technology that's evolving so quickly, and that's one of the problems right now that's holding it back. Is
from a mapping standpoint, this versus the fixed wing manned airplane is I'm guessing the size of the mapping that you have to do is probably going to be a determining factor, whether a company uses their own drone or they use.
Exactly. If you're doing 50 square miles, you'd probably want to still use a manned aircraft because you can collect that a lot quicker than this could, and how far away the project is, of course, because you got to launch this locally wherever you're going.
Right.
Yeah.
We've already approached. No, we approached and we've crashed. Now.
Yeah.
So we're actually an hour and a half. So one of the things that I'd like to cover at this particular point in our roundtable discussion is your experience with something, I don't know, it could be something recent in the past that's 3D related. So we'll go around, and Chris, I'm going to avoid letting you talk.
Yeah.
Otherwise, we'll be here till tomorrow. So we'll start with Robert. And Robert, why don't you kind of maybe talk about what you've worked with in the 3D maybe recently?
I think one of the more interesting things I've worked with was the 3D virtuality Oculus Rift stuff, and trying to see how I could implement this in a type of mapping environment. Like you told me, you had the first developer
DK
version.
one.
One thing I found though was the nausea was too intense for me to keep using that thing. I was getting really sick, but I know they have a newer version out that's supposed to alleviate that. But if we can somehow integrate, I think virtual reality with some of this 3D tech, somehow combine that with point clouds and being able to go inside a building and seeing it in 3D and virtual reality, I think that's pretty neat things that can come of that. You know.
Yeah. Did you play any games with your?
I did.
Okay.
I was really into playing games.
Were you able to play Half-Life 2?
I was. That felt really good. Half-Life felt good, but certain other games really got me sick really quick.
Yeah. Well, I will have to say that DK2 is an improvement. However, quick motion, I think the most important thing is that when you're using virtual reality, if you're not moving your feet, but your body's moving, your brain says, why are you not moving? And there's a disconnect there. And I think that's part of the
I think you're
illness. Right. And so regardless of how they fix the latency or the screen refresh, you still have to figure out what you're going to do with your feet. Maybe put yourself in a vehicle or something where you're familiar with moving without actually walking until they, I think, get past that. But in saying that, get a DK2 or even one of the phone systems. I think you can now use, is Half-Life 2 available on, I think it's available on at least the Android side now. But what I would suggest is try that with the DK2, at least Half-Life 2. I think they've also converted Aliens Isolation, which is another game where you've got a lot of structures, interior scenes that really, really, in my opinion, exploit and accentuate how VR will work. I mean, there's an example in Half-Life 2 where in the past, if you played it, you have to hook up to these health machines in order to get more health. Well, I was able to stay connected to that and move my head off to one side around a building corner and shoot off the bad guys while still staying connected. And if they shot me, it didn't matter because my health was being regenerated. I couldn't have done that without VR because I wouldn't have been able to move my head. So you really felt like you were part of that scene, and getting hit didn't do any damage because it's all virtual. So I'm waiting for the suit to be made where it'll electrocute you if you get hurt.
It is an amazing experience.
Yeah.
And I heard that the DK2 does give you like positional accuracy, correct?
Right. They have a sensor that sits on top of your monitor or a tripod that provides you that extra aspect. So you have, it gauges depth. So if you move your head forward or backwards or off to the side, you literally can move around corners and so forth. So I think that's an improvement. And the other thing that I'm going to work with, there's a Nest system that you can put transducers on your body so it knows your joints. And then obviously the Connect 2 can be used in conjunction with this to provide you an environment. And then if you remember was it the Nest? I can't remember. No, the Leap. That allows you to use hand movements, which I got a version, a little plastic headset thing that allows you to put it on top of it, and it will gauge your hand movement. And it is cool to be able to move your hands in VR and push objects. Now, there is no haptic yet, but you still get the sensation you're actually literally moving something in a 3D space. So I think it's all cool. And the important thing is it's very, very low cost.
Yeah, and if we can apply that to the engineering field, I think that'd be pretty amazing in the future. If you can, architects could go inside their buildings that they created in virtual reality. I think that's pretty neat to look forward to.
Think of it from a client's perspective. Let's say you have a client, you bring them over and you both get in the VR world and you talk about an environment. If you remember, Mike, when I set up that reality, we did some using the UDK or the Unreal gaming engine. We created an environment of both the office itself as well as an area that I don't know if they actually finished up in Atascadero, Dove Creek, if I remember correctly, and created the entire housing. And you could walk around in it, and I think we created it into a winter wonderland. But essentially, I could see from a VR perspective, you could take your client on a tour of a large, business complex and look at different things, where currently we just show video animations. So I can really see that really happening. And also in the medical, which is where I'm interested, imagine a couple of doctors looking at a 3D model of, let's say, somebody's tumor, and then be able to rotate it. And they're literally walking in their VR environment and they can zoom in and out. I see something in that particular area. And there's a doctor in Florida, a radiologist, who's really looking at moving forward with that, and got excited when I was telling him what I was able to do. And then, like you said, there are many people who are creating plugins now for different applications so that you'll be able to use VR. So really,
or even remote surgeries on top of that, virtuality type surgeries. Yeah,
it's called stereotactic, and
Yeah.
yes, there's a guy that we've interviewed who's developing and looking at sensors that allow them to get the important thing is the depth information, accurately knowing where you're at. You know, if you don't have precise information, none of that will really help. But the Da Vinci robotic system is another thing that uses stereo or 3D imagery in order to do operations using robotic assistance. That one of the doctor that we knew out at University of Pittsburgh likened it to video gaming. In fact, he said his video gaming that he played as a child well trained him for that particular position. He felt that older physicians or surgeons just couldn't get it because they didn't have that gaming experience. So let's move on to Mike. And what would you want to kind of talk about from a 3D perspective that you may have some experience with?
Well, I'm still looking at and considering the profitability of getting a scanner. And it's come, like Jesse said, it's come a long way in the last few years. Well, the downside for me was the way the software dealt with the information. If you get a scan, you're talking millions and millions of points. And granted, the field work is less, and you can acquire more information in a short amount of time. But the downside that I see is the software and being able to have some sort of artificial intelligence to know, okay, here is a sidewalk, here is a curb line, or here are these features. And why do I have to, as a human, interpret this and draw it manually? Why can't the software do that? So I'm looking forward to some sort of artificial intelligence to where we can scan and then it can artificially draw some of the line work. We as humans are going to look at that and just merely edit that information instead of having to, basically draw the whole thing line by line.
When I was more involved in it, they called it virtual surveyor. So they basically said, well, instead of having your lowest paid guy in the field deciding where to take the data points, you'd have all the data there, and you'd have someone in the office that was higher paid level person making those decisions. So basically you were taking that point data and doing the same thing we do with our robotic total stations in the field. You're just doing it in a 3D model space in the point cloud. It was very time consuming. It took you, at the end result, hours were more doing it that way.
Oh, I remember your aggravation.
Yes. And so I think the software, from what I've seen, the software has gotten a lot, gone a lot further from that, but it's still not automated. So I think, one of two things: either get more automation down, or the civil engineers say, give me a point cloud. They don't want a topo the way we derive a topo or the way Robert does it. They want that point cloud, but we're not there yet. When we get to that point, then obviously we'll be getting rid of all our robotic total stations and getting more scanners. One thing I have noticed is that, and I didn't give you PDFs for it, so you can't put it up, but I brought the paper, is that we're starting to see a lot more.
Well, you can put it between you.
Yeah, where is it? Oh, it's right here.
I tightened the shot so that
I'm managing the surveying out at the treatment plant in Los Osos. Doing all the construction staking out there. It's a sewer treatment plant, a brand new one. It's I think a $70 million project. And it's very complicated. Most complicated surveying, construction staking I've ever done.
One of these up here.
Yeah, let me show this one. So typically this is,
maybe Mike, if you can grab one edge of that and just.
This is a set of, plans. And this is, what we have to use as surveyors to do construction staking, so that they know where to.
Go ahead and lift it up a little bit. There you go.
So that they know where to, put everything and build everything. So this is a concrete foundation, and you have the tank there, and it's very complicated to look at, and to build. Well, then they give you these nice 3D renderings, and they're actually designing this in 3D. They're not doing 2D drawings and then 3D renderings. They're designing everything. The mechanical engineers are doing this in three dimension. So when you get these views, it makes it a lot easier to understand what someone's building. Makes it a lot easier to provide layout for that. we're starting to see a lot more of this in our industry.
Do you know what
design side.
application they use to design those?
Yeah.
That's what I was hoping you would say.
Yeah. So, but this is in CAD. I get the CAD drawings. It's wireframe in CAD, mechanical. You know, the plant has.
So do you get a DWG?
Yes, DWG. The plant has parts of the plant that are 4 stories. 3 stories are underground by the time when it's finished, when it's built, and it's all, you know, most of the CAD I was given was done in 3 dimensions, so you'd see the whole thing in 3 dimensions, which is,
so even though you're well trained to look at 2-dimensional drawings and derive 3D, it is always better to be able to see something as it really will exist. I mean, that's we're wired that way.
Right.
Yes.
And you know, that's interesting because in the medical field, we were finding the same thing, even though physicians or especially surgeons say, well, I'm used to looking at 2D radiology images and I can come up with what I need to. But some of them say, no, that 3D perspective is always important. So like anything, it's like adds to your toolbox. So, and as you showed us there, what you could see from above and then what you could see in 3D really, as you said, will make it much easier for you. So on that note, I'm going to skip Chris because he can talk more on Friday. We also do a few others, and I'm going to bring them up. This Thursday, we're going to be doing a interview with somebody else who's designed a compact portable mobile 3D scanner, and it's for Android. So it'll be really interesting. It's somebody out of Ohio. I found them. I don't know how I came up with them. So I've invited him on, and we'll do an interview with him on Thursday. The name of his company is Knockout Concepts, and his name is Brooke Myers. So we look forward to that on Thursday at 10 a.m. And then we bring on our guest crashers for our Friday show, which is 3D in Review, Javis Jones, who is the one of the developers for a product called 3D Coat, which is something that I use repeatedly. And it's an organic 3D mesh painting tool as well as a deformation tool. So it's like sculpting with your 3D. And so it's really, really powerful. And if you're into 3D modeling, you know, I think it's the go-to product since it's only $100 for their educational or Steam version. I think it's $400 for the professional model. So it's very, very reasonable. And next week, we have an exciting day. 3D helper Santas. Now, Santa helpers are going to come out and we're going to be looking at SLA printing. I can't show the camera, but we're going to be looking at the little RP. I've never, I bought it. It's sitting there. It's never been used. So we're actually going to get it up and running. So Chris is going to come join me.
Show you how to start from scratch with a little RP, which is a great little SLA printer. I've been printing on mine, but we'll show you step by step how to get it up and running.
Yep. And we're going to have Brad Hill, who's the designer, who's going to be joining us via Google Hangouts on Air, as well as the designer of the software creation workshop. So we're going to have the whole team here. So if you've never done SLA printing, you're going to know how after that
Join
episode.
us in the chat room.
Yep.
Ask us your questions, whatever you need.
And the other thing that we're going to be doing is FDM. We're bringing back on Dustin, who I interviewed. I actually was our guest crasher last Friday. He does a product called Simplified 3D. Chris is going to come in and we're going to do some FDM printer. I've got, I think we're going to use the Maker Gear M2, but we're going to go through on how to set it up, calibrate it, and then print something. So if you're into FDM or SLA, it's going to be a great day next Monday because you know what's going to be under your Christmas tree on Thursday. Okay. On that note, I think that's about it. Chris, why don't you kind of
all right. Well, thank you so much to our in-studio guests today. We learned a ton. I am just really looking forward to working with you guys moving forward and hopefully get some projects going with you guys. And so just want to thank our listeners for joining us on another episode of All Things 3D. We'll see you on Wednesday.
Bye.